Some transition metals like iron, cobalt, and nickel are ferromagnetic transition metals. For IV chemistry, each of these properties in detail. In this lesson, we will cover the electronic configuration of transition metals, properties such as variable oxidation states and color, complex ion formation, ligand types, isomerism in complex compounds, and practical applications. Transition metals are elements with incomplete d subshells in at least one of their oxidation states. The first row transition metals are from scandium to zinc in the periodic table. Their general electronic configuration is of the form 3d to 3d10, 4s2. However, note that chromium and copper have exceptional configurations due to the added stability of half-filled and fully filled d subshells. Chromium has configuration 3d5, 4s1 instead of 3d4, 4s2. Copper has 3d10, 4s1 instead of 3d9, 4s2. These exceptions are important for understanding the properties of these elements. Transition metals exhibit several characteristic properties. First, they have high melting and boiling points due to strong metallic bonding involving d electrons. Second, they form colored compounds. Third, they show variable oxidation states. Fourth, they act as catalysts. Fifth, they form complex ions with ligands. Sixth, they show magnetic properties. Some transition metals like iron, cobalt, and nickel are ferromagnetic. Let us explore each of these properties in detail. One of the most important features of transition metals is their ability to exhibit multiple oxidation states. This is because the d electrons can be involved in bonding. Let us look at some examples. Vanadium can show oxidation states from +2 to +5. Manganese shows states from +2 to +7. Iron commonly shows +2 and +3, though +6 exists in ferrate ions. The most common oxidation state for copper is +2, though +1 exists in some compounds. The relative stability of different oxidation states depends on the ligand environment and can be predicted using redox potential diagrams. Transition metal compounds are often colored due to d-d electron transitions. When visible light passes through a compound, electrons can be excited from lower energy d orbitals to higher energy d orbitals. The energy difference corresponds to a specific wavelength of light, which determines the color we see. The color depends on the metal, its oxidation state, and the ligand. For example, copper 2+ ions are blue, while copper 1+ ions are colorless. Iron 2+ is pale green, while iron 3+ is yellow-brown. The color can be explained using crystal field theory, which describes how the d orbitals split in energy in the presence of ligands. A complex ion consists of a central metal ion surrounded by ligands. Ligands are species that donate a pair of electrons to the metal ion. They can be classified based on the number of donor atoms. Monodentate ligands donate one pair of electrons. Examples include water, ammonia, chloride, and cyanide ions. Bidentate ligands donate two pairs of electrons. Examples include ethylenediamine and the oxalate ion. EDTA is a hexadentate ligand that can donate 6 pairs of electrons. The coordination number is the number of coordinate bonds formed by the central metal ion. Common values are 4 and 6. The shape of a complex ion depends on the coordination number. With coordination number 6, the geometry is octahedral. With coordination number 4, there are two possible geometries. Tetrahedral geometry is common for 4-coordinate complexes with small ligands. Square planar geometry is favored for D8 metal ions like nickel 2+, palladium 2+, and platinum 2+. Examples include the tetraaminocopper 2+ ion, which is square planar, and the hexoquaran 3+ ion, which is octahedral. Complex ions can show several types of isomerism. Structural isomerism includes ionization isomerism, where isomers produce different ions in solution, and coordination isomerism, where ligands exchange places between metal ions. Stereoisomerism includes geometric isomerism, which is common in square planar and octahedral complexes. For example, the diaminodichloroplatinum 2+ ion can exist as CIS and trans isomers. The CIS isomer is used as an anti-cancer drug. Optical isomerism occurs when complexes are chiral and non-superimposable on their mirror images, like the tricephalinediamine complex. Ligand substitution reactions involve replacing one ligand with another. There are two main mechanisms. The associative mechanism involves the incoming ligand first attaching to the metal, forming a higher coordination number intermediate before the leaving group departs. This is common for square planar complexes. The dissociative mechanism involves the leaving group first departing, forming a lower coordination number intermediate before the incoming ligand attaches. This is common for octahedral complexes. Whether substitution proceeds quickly or slowly has important applications. For example, the Cisplatin drug must undergo slow ligand substitution to be effective. The stability constant, or formation constant, measures how stable a complex ion is. For a general complex formation reaction, the stability constant Kf equals the concentration of the complex divided by the product of the metal ion and ligand concentrations. Larger values indicate more stable complexes. Stability constants can be used to predict whether displacement reactions will occur. A more stable complex will displace a less stable one. For example, the cyanide ion can displace ammonia from complex ions because the cyanide complex is more stable. Transition metals and their compounds are important catalysts. They can act through several mechanisms. First, by providing a surface for adsorption, like iron in the Haber process. Second, by forming intermediate compounds, like manganese dioxide in the decomposition of hydrogen peroxide. Third, by changing oxidation state, like vanadium pentoxide in the contact process. Catalysts are essential in many industrial processes, including ammonia synthesis, sulfuric acid production, and petroleum refining. Transition metal complexes also act as catalysts in biological systems. For example, hemoglobin carries oxygen. Transition metals have numerous practical applications. In medicine, cisplatin is used in cancer treatment. EDTA is used to treat heavy metal poisoning by forming stable complexes that can be excreted. In industry, titanium dioxide is used as a white pigment in paints. Vanadium pentoxide catalyzes the production of sulfuric acid. In technology, nickel-cadmium and nickel metal hydride batteries use transition metals. Iron is essential in steel production. These applications rely on the unique properties of transition metals. Let us try some practice questions on transition metal concepts. Question 1. Explain why chromium has an anomalous electronic configuration. Question 2. State the coordination number and geometry of the complex ion formed when ammonia ligands replace water ligands around copper 2+. Question 3. Describe the difference between a monodentate and bidentate ligand, giving one example of each. Question 4. Explain why transition metal complexes are often colored. These questions cover the key concepts in this topic. To summarize the key points of this lesson. First, transition metals have incomplete d-subshells and show variable oxidation states. Second, their compounds are colored due to d-d electron transitions. Third, complex ions form when metal ions bond to ligands. Fourth, ligands can be monodentate, bidentate, or polydentate. Fifth, geometric and optical isomerism occur in complex compounds. Sixth, transition metals and their compounds are important catalysts. Remember to practice past paper questions to master this topic. Thank you for watching this lesson on transition metals.